All right, let's see if we can come up with a formula for the sum of a geometric series. So if I was to write the sum out, the first term would be a, then ar squared, all the way up to ar to the n minus 1. I'm going to rewrite this one, but I'm also going to multiply it by r. You'll notice I've just shifted them along a little bit to sort of show you why. Because when I multiply the a by the ar, so I've lined it underneath the ar, and the ar with the ar squared, and so on, and unfortunately the spacing didn't quite work nicely enough, but the ar to the n minus 1 should be under the ar to the n minus 1, and we'd be left with this new ar to the power of n at the end. But we could create, again, simultaneous equations now. So I could subtract, and I'll get r minus 1 lots of s to the power of n, so it's the bottom one minus the top one, would be ar to the power of n minus the first term, a. And all we've got to do is play around with this, and we come up with a formula. So factorise the a, and then divide by the r minus 1, and there's our formula for the sum to n. A outside of r to the power of n minus 1 over r minus 1. The thing to be careful with this formula is because we're so used to seeing power of n minus 1, when we say r to the power of n minus 1, we're not saying r to the power of n minus 1, we're saying r to the power of n minus 1. Okay, so be careful with that. That formula we tend to use if our ratio, and I'm more talking about the magnitude of the ratio rather than plus or minus, is greater than 1. Okay? If it's less than 1, we switch them around and go 1 minus r to the n over 1 minus r. Because when you think about it, all I've really done is multiply top and bottom of the fraction by negative 1. So it is the same thing. And the main reason for doing that is because this one I would use if the magnitude is like less than 1, so in between minus 1 and 1, so we've got a fraction. And I guess the only logic behind it is so you end up with a positive number on the bottom. Because if you go 1 minus a fraction smaller than 1, you're going to get a positive number. Whereas on the top one, if you've got a number bigger than 1, you'll get a positive number on the top. That's the only logic. The reality is it actually doesn't matter which formula you use, because of course they're the same formula. We also have a special one in geometric ones. It is actually possible to add up an infinite number of terms. So even though the series never ends, it is possible to get a finite answer. So sum to infinity, also known as the limiting sum. But it's only possible if that ratio is in between minus 1 and 1. So if you like, when you're multiplying, the terms are becoming smaller and smaller and smaller. And so if you think about that, if they're becoming smaller and smaller and smaller, as you head out to infinity, then the terms are getting closer and closer to 0. And so that's why we can add up an infinite number of terms, because theoretically, if we could get to infinity, we'd be just adding 0 on. Now, what I do know is the limit as r to the power of n, as n approaches 0, remember, r is in between minus 1 and 1. If you think of your exponential curve, but this is the exponential when the base is a fraction. So it's like saying, instead of saying 2 to the power of n, we know that would be something like y equals 2 to the power of n. But we're saying the base is a fraction, so it's like having a negative power. So that would be, say, a half to the power of n. So as n is approaching infinity, we can see from our curve that that is approaching 0, the actual y value. So if r is, in fact, in between minus 1 and 1, then the limit as n approaches infinity of r to the power of n equals 0. That idea allows me to come up with a formula. Because remember, our formula is a, 1 minus r to the power of n over 1 minus r. But we're saying the limit as n approaches infinity. And so that r to the power of n part becomes 0. And so it's a on 1 minus r. Because now there's nowhere to substitute n in, so it doesn't matter that there's an infinite number of terms. We've used the limit to substitute in for the n, and we've got our formula. So our sum to infinity, or our limiting sum, is simply a over 1 minus r, but again, that ratio must be in between minus 1 and 1 for the limit to exist. Okay, so we're going to find the sum of these ones, 2, 6, 18, and so on, but the first 10 terms. So now the first term's 2, ratio's 3, and we're saying the number of terms is 10. So I'll use the r to the n minus 1. Subbing in, It depends how good your calculator is. I suppose I've been doing these for so long. The calculators that were around when I started doing these were very basic, so I tend to work out the bottom first, do some cancelling, and then go through to the power of 10 minus 1. But these days you can probably do it all in one hit. And however you do it, it ends up being 59,048. Some notation. This one is geometric. I can tell because the n is in the power. So remember the general term is AR to the power of n minus 1. So you see the n in the power, then we know that's going to be a geometric one. Notice we're not starting at n equals 1 for this one. We're starting at n equals 3. So what do we know? Well, if you're unsure, then just write out a couple of terms. So the first term, remember, is when n equals 3. So that's 6 to the power times half squared. So that works out to be 3 on 2. The ratio is going to be a half, because that's what each time we're multiplying by half. We know that because it'll be r to the power of. And the number of terms, be careful, 8 minus 3, but it's inclusive, so we've got to add one. So there'd actually be 6 terms all up, not 5. Okay, let's sub it into our formula then. All right, again, depending on how good your calculator is, whether it handles all these fractions to a power over fractions, I probably would tend to go 1 minus a half is a half. The 3 on 2 cancels with the half to give me just 3 times this expression. And in fact, there you go. There's the 3 on 2 divided by a half, where I've inverted and multiplied. I worked out inside the parentheses. That turns out to be 63 on 64. And then I've done it that way. Again, that's just me because of the way I started doing these when I first did it. The technology wasn't as good as it is now. Quite possibly you could just chuck that all into a calculator and get the answers, because these days they even leave them as fractions. The early calculators, they'd spit out a decimal answer for something like that. So the question is, does this particular one have a limiting sum? So 56, then 4, then 2 sevenths. So remember, the key is, what is the ratio? That's what they're getting at here. They want to see if you understand that the ratio needs to be in between minus 1 and 1. So the ratio for this one is 4 on 56, but a good thing to check, whether you write it down or do it in your head, check it for the other terms as well. Make sure they're not tricking you, and make sure it is a geometric series. But 2 sevenths divided by 4, sure enough, it does turn out to be what we need. But that is less than 1. And so, yes, it will have a limiting sum. So I say yes, and I give the reason why, because that ratio is in between the minus 1 and 1. The frog in the well. There's one of these paradoxes, you know those stories where you got a frog in a well, and it jumps up, but it can only jump up half the height of the well. And then the next time it does it, it can only jump half as much as it did before. And the question is, does it ever get out of the well? And the answer actually is no. It's a very stupid frog. Because when you think about it, it's got a quarter of a distance, then an eighth of a distance. At some point, it's going to be that close, but it can only jump half as what it did before. It's going to, oh, damn, still can't get out. Yeah? Because if you look at A is a half for this one, the ratio is also a half. So if it did an infinite number of jumps, A on 1 minus R, we get a half on 1 minus half, which is just 1. So it'd be very frustrating for our poor frog. He gets right to the edge and, nah, can't get out. We've seen this question before, of course, and hopefully we remember the quick way of doing this, and we can look at this and just say the answer is, yeah, so 36 on 99. We also saw how to do it via simultaneous equations, you remember. There's now a third way of doing it. If I saw the question like this, where it simply says write as a fraction, I'm going to write 36 on 99. I'm just going to write the answer down. Sometimes they'll say it by expressing it as an infinite series or something like that. Because remember, 0.36 repeater is an infinite series. You could write it as 0.36 plus 0.0036 plus 0.000036 plus 0.00000036 plus 0.0000000036 plus 0.0000000036. I think you get the idea. And so what we actually have is a geometric series there. The first term is 0.36. The ratio is 0.01. And so I can use my infinite series formula, A on 1 minus R, and we get 0.36 on 1 minus 0.01, which is, well, it's actually 0.36 on 0.99, but we don't write fractions that way, so multiply top and bottom by 100, and we get 36 on 99, the answer we were expecting, which of course cancels down to 4 on 11. So make sure you read the question. If it says by expressing as an infinite series or something like that, then they want you to use this formula to come up with the answer.